Welcome everyone. It's very strange for me to be presenting in front of a camera instead of the live audience of the 20th Plastic Pipe Conference in Amsterdam, the Netherlands this year. Nevertheless, I'm really excited to have this presentation here about the pipe test for polyethylene pipes with a raised resistance to slow crack growth. My name is Ernst from Stok. I work as material scientist and consultant at Kiwa technology here in the Netherlands. And I really have loads to tell you. Unfortunately, I only have 15 to 20 minutes to give you this presentation. So please read my full paper to get all the details. I'll try to give you some highlights in this presentation. And well, like I said, it's about two pipe tests. The first one is the accelerated notched pipe test. The accelerated notched pipe test is to measure the pipe's resistance against the surface damage. For instance, because of a scratch due to pretentious installation. And this scratch can, of course, grow further. This can crack the pipe eventually. So the pipe measures the resistance of the material against it. The other test is the point load test. In this case, the polyethylene pipe is installed perfectly well and it's all undamaged. But now somehow a point load, such as a stone, presses upon the pipe, and therefore you get tensile stresses on the inner wall of the pipe, and therefore you may have a crack. So the point load tests the material's resistance in this case. So I'll try to give you in this presentation an overview for both tests about the test method, the equipment we're using, and their tests are still under development. So we have a lot of lessons learned, and I really like to share that with you so we all can benefit from it. Of course, I'll also try to give you some results. They're actually quite interesting. So let's go through it. First up is the accelerated notch pipe test. Or perhaps better, let's start with the normal notch pipe test. So what's the normal notch pipe test? Well, here you see a plastic pipe, a polyethylene pipe, which is installed in the water bath. And we have 4 notches in the circumferential around it. The water bath is at 80 degrees centigrade, so we have a higher temperature to accelerate it. We have a pump to pressurize the pipe. So it's sort of hydrostatic pressure test, but now we have 4 notches on the circumference. The only thing is that it's for that pipe, polyethylene pipe with raised resistance to slow crack growth, that it takes just too long to let it fail within a reasonable time. So what can we do to accelerate it? Well, we put in a detergent. So now the pipe is not submerged in water, but it's submerged in a detergent solution. And that will accelerate the test spectacularly. And this is also being standardized. So the notch pipe test is already in ISO 13479. And this will be standardized in a separate annex and will be published soon. And please note that although the pipe is placed in a detergent solution, inside the pipe is still water. So we're not placing detergent solution inside as well. It's just outside the pipe. Now, the only problem is with the detergent solution on the outside of the pipe is that it's a water tank of 1800 liters. And the detergent used is alcohol. And alcohol is toxic and bioaccumulative. So that means that it's not really friendly to dispose after every test the 1800 liters of detergent solution. So we wanted to make a more eco-friendly test. So what we did is made a smaller container. Smaller container just has 30 liters of detergent solution and is perfectly well fitted to hold the pipe and accelerate the test in a proper way. The only point here is that alcohol also sinks to the bottom if you're not letting it flow. And normally it's in the water tank, so normally it's all circulated because of the homogeneous temperature we're needing. But now within that smaller container, we don't have that circulation. So in this case, we added a separate pump to circulate the detergent solution inside that smaller container. But it's of course very important that it's homogeneous and that the detergent really reaches all the notches and is not only aggressive to the notches on the bottom side of the pipe and not on the top side of the pipe. So therefore we did some extra tests. So how did we do it? We simply replaced the detergent by colorant. So we have a green colorant and we tested the circulation equipment to see if the colorant is really distributed a little bit turbulent and really gets the solution homogeneous. So we made a video of it and I'd like to show it to you right now. So here we see that smaller container, we see a polyethylene pipe in the middle and we have end caps. And what we're doing now is we're letting that detergent solution entering that container. So you see really, it's not the detergent solution, is the colorant. So here you see the green colorant really circulating very nicely around that pipe. It comes to all the areas in the smaller container. So actually in a few minutes time, the complete container is completely green and it's all homogeneous distributed. So that we were very happy with it. It really gave a good sense that we are very good circulating that detergent solution inside our smaller equipment and that it will work very fine. And we also therefore participated successfully in a round robin that was organized by the P100+ Association. So we're really confident that we're performing this test in a proper way. So what about some results? Well, here I show you a picture of a failed notched pipe test, accelerated notched pipe test. It's made from the inside of the pipe. So we're looking at the inner wall of the pipe and we actually see two notches, which is sort of strange on one hand because the notches are made on the outside of the pipe. But now we see the notches on the inside. And of course, it makes sense if the notch failed, but the other notch we are seeing did not fail. And the other two, because there are 4 notches, the other 2 we couldn't see on the inside of the pipe. So that seemed to be interesting. What we did was we made a cross-section of those notches to see what is actually happening here. Now what's happening here? Here you see that pipe wall thickness. So you see just the pipe wall and on the bottom side here is the notch. And what we see further on, well, we don't see anything on the inner pipe wall. So this was one of those 2 notches that didn't crack completely to, or we didn't see on the inner side wall. But what's very interesting, and it's very difficult to see, but you can see it quite clearly on a microscope, is that there's actually a fine line over the ligament. So starting from the notch to the inner pipe wall. And this is actually quite strange. I was quite surprised by it because you would expect that a crack would start at the notch tip and you would see something there. But now suddenly we see over the entire pipe wall, before it even failed, we already see a fine line. So apparently something is already happening on microscopic scale simply due to increased stress in this area. Now if you go to the other notch that didn't fail, but we did see on the inside, we see this cross section. So again, we see the pipe wall, on the bottom side we see a notch, and in this case we do see a starting crack. But the crack isn't completely through the pipe wall. It's just a starting crack. Then we have that fine line again, and then something strange happens again, because on the inside of the pipe we suddenly see some indentation, some ductile flow apparently. So a pipe wall has residual stresses due to the production, and we have compressive stresses on the outside and tensile stresses on the inside. So apparently, because the crack is starting, those stresses have to redistribute over the pipe wall, and therefore we get an indentation or some flow of material on the inside because of the residual tensile stresses. Now the final crack that we can see here, because it completely went through. Here we see the notch, we see a crack, and we see some ductile behavior on the inside. The crack is slow crack growth, so it's really brittle, but the end part, the ligament, is then so small that the pressure will deform it ductile. So we thought these are really interesting results because they gave us a very nice insight in the failure mechanism of the polyethylene pipe in the accelerated notch pipe test. So this was a really quick overview of the accelerated notch pipe test to simulate a scratch already in the pipe due to, for instance, transstress installation. But now what about the other test, the point loading test? The point loading test is actually also a hydrostatic pressure test. So again, we have that polyethylene pipe, we have those end caps, we have a pump to pressurize the pipe, we have a water tank, which can be 80 or perhaps even 90 degrees. But in this case, we don't have any notches on the pipe itself. We have a point load. And on the other hand, a support, of course, otherwise you're just pressing the point inside the pipe and the pipe will bend. So you have to support the pipe. Now in this case, it will just take too long to fill it like this. The temperature isn't enough to accelerate the test properly. So we need the detergent again. But in this case, the tensile stresses due to the point load come from the inside. So therefore we need that circulation pump again. And that will distribute the detergent through the pipe. And then we have detergent inside the pipe in this case. So this is a picture of our test setup. So you see two end caps of the pipe, which have those hoses to circulate the detergent. It also has a connection for pressurizing the pipe. And we have the point load. Here you can see it, and of course the support. So it's difficult perhaps to see. So here's a bigger picture. So this is where the pipe is placed inside. The point load has a tip radius of 5 millimeters, so the diameter is 10 millimeters. And it actually, in theory, it's a quite easy test. But it's still under development. We are working with it with two other labs, SKZ and TGM, and it's quite difficult to get it working. Now, what was the first problem, for instance, is the detergent. The detergent we were using in the beginning was Detergent at 90 degrees. So what did Detergent? It attacked all our rubber connections. So we have all the rubber, like Viton, for instance, and these are pictures by SKZ, and Viton rubber is attacked very strongly by Detergent at 90 degrees. So all our quick fix connections started leaking. We have everywhere where rubber is used, also the circulation pumps, for instance, they're using rubber. We have to replace them. So for instance, the quick fix we replaced by simple screw connections, but the rubbers in the pumps, we replaced them by EPDM, which have had a much better result and were much more resistant to Detergent. The second point is, how is the flow of the detergent inside the pipe? It must be turbulent. It must get to that pipe, to that inner surface where the point load is pressing on. So what we did, we made a sort of internal spray system, which is already used by one of the two other labs. So here you see it. It is an end cap. Then you have sort of rigid hose, which has some exit holes on the outer end for the detergent. And we have a block, so really the detergent is forced exactly at the spot where the point load is. So this is what we did, still under development. We did already quite some tests, especially on the first generation polyethylene that is used in the Netherlands. So that's really the polyethylene pipes that are already installed like 50 years ago. We already published it, and these are, well, the latest results. So what do we see here? First of all, on the vertical axis, we see the failure time of these pipes. On the horizontal axis, we see the hoop stress. So the internal pressure actually of those polyethylene pipes, but it's corrected for the wall thickness. Of course, a pipe with a smaller or thinner wall will have, under the same pressure, more stress inside the material than a thick wall pipe. What you see here is all those dots are those failure times of first generation polyethylene, but they're multiple polyethylene pipes from multiple locations in the Netherlands. Some were more used than the others. They have different SDR classes. We sometimes use different indentations for the point load. So we have different results here, but it still gives you a good idea, and you see really that there's a dependency on the hoop stress. So the internal pressure of those pipes depends on the failure time, or it gives the rise to the failure time. So actually one of the advices also to the end users or the pipe owners was also, if you have problems with point loads, reduce the pressure, the internal pressure. That really helps. But we also sort of extrapolated it. It's because we did it at 80 degrees, at 60 degrees, at 40 degrees. So you can extrapolate it to soil temperature, and we can take into account the acceleration factor of the detergent. And then we can see, okay, what time would it take for first generation to fail due to point loads? And that came actually it was in good agreement with practice. Because if we extrapolate these results, we came at 35 years. And the first point loads failures in the Netherlands were after about 35 years being in use. So it really gave us confidence that we really get a good result here with the point load test. But of course then the pipe owners asked, okay, that was the really old generation polyethylene pipe. What about the second generation? So the P80, the high density P80s. These pipes do have a comonomer inside, but they're not with a two-step polymerization process. So they're not really linked to the longer chains, the polymeric chains in the material. So what about those second generation? So we tested them as well. And these are the results. So what you see here, again, on the vertical axis, the failure time and the hoop stress, and we don't on the horizontal axis, and we don't see any dependency on that hoop stress anymore with the second generation. We also didn't test the 40 degrees because it would take too long to test. And with that, you already see that improvement in material. You see it even better here. So in this graph, I just show the 80 degree centigrade lines, so the 80 degrees. And what you see that the second generation polyethylene is 6 to 12 times as good as the first generation. And if we look at that for the 60 degrees lines, we see it even increases. So it's even better at 9 to 19 times better, the second generation. So we could again extrapolate that. And what we saw is that, or what our advice is, we don't expect any point load failures in the next decade for second generation pipes. Of course, exceptions could take place and incidents could take place. And second generation polyethylene isn't really designed to be installed with point loads such as P100RC. So what about P100RC? Because you already see we're almost going to the 1,000-hour line for second generation, and P100RC, we really have a lot of difficulties to get that correct acceleration. So we're still looking for the right test parameters. Which temperatures do we need? Which detergent do we need? But first we also have a little bit of step back. What is the agreement between these three laboratories, Kiwa, SKZ and TGM, about how is our failure times, how do they correspond with each other? So that's what I'll show here. So here you see for two materials, which are coded 266 and 268, and the failure times in these three labs for P100 grade. And this is tested with Arcopol. So you see that the failure time is a little bit higher because Arcopol isn't so aggressive to the polyethylene. And actually what we saw is that the scatter within one laboratory is really low. So we're really happy about it. It's really good. Between the three labs there is some scatter, but on the other hand that's also normal for normal hydrostatic tests. You have the same amount of scatter with the notch pipe test, for instance, or the accelerated notch pipe test. But nevertheless, we had a lot of good discussions since the results, really improving the test method and harmonizing it more. Great thanks to the ISO working group where we had those great discussions. So we're quite confident if we have that better detergent to accelerate the failure time even more, that the scatter between the labs will also be much smaller. So that concludes my presentation. I've shown that the accelerated notch pipe test and the point load test are really two promising tests that are still under development, and they gave great acceleration to test polyethylene with raised resistance to slow crack growth. So please stay in touch and don't hesitate to contact me or my colleagues if you have any further questions about these topics.